Right, 93, this was the silver dollar falling from the sky. So we kind of started this one already on Friday.
I mean, I remember how we talked about it. It was like you derive something, but I didn't remember what gave you what gave you what.
Okay, well this is the position function. All right, so when part A says determine the position function for the coin, we've already got that.
Okay.
Right, so if we want the velocity function, we take the derivative of this. So I'm going to get negative 32t plus initial velocity. That's part A. Part B says determine the average velocity on the interval 1 to 2. Right, so we're talking about average velocity on the interval 1 to 2. That's what we just did in the last problem. What's my B?
Which one are we putting it into?
This one. We want the average velocity.
Okay, so it's going to be negative 64 plus 0. Or,
well, if what is going to be the initial velocity if I'm dropping this point? 0. So the real equation here.
so is it going to be negative 32 for A and then negative 64 for B?
Yeah, so we're not really plugging it into that one. We're really plugging it in here. So my B is 2, my A is 1, and then my f of B is when I plug 2 into that, so I get negative 64, minus when I plug my A in there, I get a negative 32. So I'm going to end up getting negative 32 over 1. Negative 36.
So that's the average velocity.
That's the average velocity on the interval 1, 2. Now it says find the instantaneous velocities when t is 1 and when t is 2. Right? That's when. So that's just taking this derivative here and plugging in 2 and 1 and seeing what I get. So when I plug 2 into that, v of t, v of 2 I guess, is going to be negative 32 times 2, which is negative 64. And v of 1 is going to be negative 32 times 1, which is negative 32. D, find the time required for the coin to reach ground level. Right, so now we're talking about ground level and I want to search for time. Which equation should I be using?
First one.
Yeah, because we're looking at position now. Ground level, that's a distance. So at ground level, what is my end height? 0. So when 0 equals negative 16 t squared plus my initial velocity of 0t, so I don't even need that, plus how high was the coin? 1362. So we want to solve this. So if I subtract 1362 from both sides, divide both sides by negative 16, t squared is going to come out to be 85.125. Yep, take the square root. T is going to equal the positive and the negative of 9.2-ish. Okay, now, I got two answers for that. Which one's out?
Negative.
Yeah, because they can't have negative time. Not yet, unless you invent the time machine. We've got to go with the positive one. Okay, so that's how long it's going to take, 9.2 seconds for that coin to hit the ground. And then they say find the velocity of the coin at impact. So what do we do with that 9.2?
Put it in here. So.
Yeah, we plug it back. We plug it up into that one with the V of t. 9.2 of negative 32 times 9.2. Negative 295.24, and then this is feet per second. So does that mean that it's like really slow since it's negative? Why is it negative?
Because it's going down.
Because it's going down. The negative is for direction. Good. That would make a little more sense to you now, that how...
I didn't know which was position and which was velocity.
Yeah, position will be x, and then they may or may not write v of t like I did, but you know that s prime of t, which is the derivative of s, will give you the velocity.
Right.
And s double prime
Is,
acceleration. So you'll just end up with that negative 32, and that makes sense, because the acceleration of gravity is negative 32 feet per second per second. All right.
today's stuff.
For these true and false questions, all you have to do is just show one case that it's not going to work, and that's false. Okay, so for the first one, 83, it says if f prime of x equals g prime of x, then f of x equals g of x. All right, and what did you put for that one? True. Okay, but it's false?
Yeah.
Okay, I agree with false. All right, because think about that. You can get the same derivative for two different functions.
Okay.
And I'll try to keep it simple here for you. All right, so let's say that f of x is x squared plus 7, and g of x is going to be x squared plus 9.
Oh.
Same function?
Thing.
Nope, but the derivatives are going to be the same, aren't they?
Good.
Yep, because you're both, when you take the derivative of x, you're going to get 2x, and when you take the derivative of g, you're going to get 2x. But that didn't mean that the original had to be the same. Kind of tricky. 85. Right, if y equals pi squared, you're going to kick yourself on this one, by the way. Then dy over dx, which is just another way of saying the derivative of, is 2 pi. What's pi?
Oh, it's a number.
It's a number. It just looks like a variable.
Oh,
I know.
numbers.
Tricky. All right, so what is the derivative of pi squared? No, it's something. It's 0. So that's why that one's false. All right, now 87 is kind of an interesting one. It says if g of x is 3 of f of x, then g prime of x is going to equal 3 times f prime of x.
Which to me, that just doesn't.
Well, first of all, let's use a specific example, and then we'll talk in generalities. All right, so a specific example, let's say that g of x is x squared plus 2x plus 4. Okay. Well, then we're also saying that g of x is, take that back. That's going to be my, all right, so what's g of x going to be, man?
3 times.
Yep, so 3x squared plus 6x plus 12.
Okay. Oh, I just don't fuck.
All right, so take the derivative of f of x.
2x plus
2x plus 2. Take the derivative of g of x.
6x plus 6.
So is the derivative of g, which is 6x plus 6, equal to 3 times the other one?
Yes.
Yes, it is. Now, it could just be coincidence that I randomly selected and made up my own. I made up my own functions and it worked.
Yeah.
Or it could mean something that I randomly selected it and it worked. It means something. So let's think about it a little bit differently. So if you look back at your rules for taking the derivative of something,
Take the power multiplied by what's it?
right? So if you have 3 times the derivative, you're allowed to take the derivative and then multiply it by the 3. That was one of the properties that we dealt with. That's why it works.
I think I follow on this. It's just not what I was expecting.
Yeah, use specific examples for those true and false. You only have to prove it wrong once.
Okay.
If you're just randomly picking functions and you can't prove it wrong, chances are that's because it always works.
Okay.
All right, then you just have to kind of come up, you have to reason out why it always works. This one is because of a property. Right? But the other two, especially 85, that's a very common mistake. I've got people taking the derivative of pi all the time, thinking it's a variable because it looks like one. You want to do that, but it's not a variable.
Had I actually thought that one out a little bit longer, I probably would have. Yeah.
I like 83 as well because it really makes you think about those concepts.
It just
Sort of. Yeah, it's going to be the same when we're taking the integral later on and going backwards. That's going to play an important role to our solution. We're not going to know what that constant is, so we're always going to have to put a plus c for constant. So your curve, you may figure out what the shape of your curve is going to be, but you don't know if it's going to be here or up a little bit higher or up here. You just have the shape, and then it depends on where its vertical position is like that. All right, not too bad.
Yeah.